Okay, so coordinate covalent bonds are something that we see when we are dealing with covalent molecules. So when we're dealing with covalent molecules, we are sharing electrons. Okay, last video we talked about lone pairs and we talked about bonding electrons. So most of the time when you form a covalent bond, it's because you have two atoms that each have an unpaired electron or a bonding electron, and those bonding electrons are going to come together to create a pair. But in some cases, what winds up happening is one atom donates both electrons to the pair. So instead of it being this atom has its unpaired and the other atom has its unpaired, instead what happens is one atom with a lone pair, which normally doesn't participate in bonding, winds up turning that lone pair into a shared pair, okay? So it doesn't change your diagram, how you go about doing it. It's more just sometimes what happens is you guys start drawing things. In particular, if you think about kind of the last example that we ended with yesterday. So yesterday we had that CO3 molecule, right? So we had the C, we had the O, we had the O, and then we had this, we had this, we had this, and this, right? And then obviously these had their electrons going on as well. And so what happens, and some of you notice this and some of you be like, I honestly didn't notice that, and that's totally fine too. So this O here did what we expected it to do. And why I say it did what we expected it to do is oxygen has 6 valence electrons. It has 2 which are unpaired. So it makes sense that oxygen would form 2 bonds because it's going to pair up each of its unpaired electrons. But if you look at these two O's, they didn't do what we expected them to do, right? If you look at them, they have 6 electrons, all here, but they didn't share. And then there's carbon here with its 2, right? And so this is where this molecule did have a charge associated with it because it had that -2, which meant it had 2 additional electrons, which kind of went onto the carbon. But what happened is this oxygen and this oxygen basically did a coordinate covalent bond. They donated nothing to this shared pair because they started with 6 valence and they still have 6 valence, right? This one did donate though, right? Because it started with 6 and now it only has 4 that it's kept to itself and it's sharing the other 2. So in this case, these oxygens, for lack of a better description, are basically mooching. They didn't bring anything to this partnership. They just said, hey, you have some electrons? I would like some electrons. And they kind of just attached on. So does it change anything about the diagram? No, because you were able to draw this diagram yesterday before you even knew about a coordinate covalent bond. It's more just sometimes some of you are like, this doesn't make sense. Like, why did this do this? I know that it shouldn't have done that. And coordinate covalent bond kind of explains that, where you'll see that sometimes certain atoms don't make the number of bonds we expect them to make. And that is because they don't end up donating to the shared pair. Instead, they just latch on to a lone pair and consider it a shared pair. So example here of nitrate, right? So think about nitrate. We want to go through all our different steps to draw our diagram. So N is going to go in the middle because it has the most unpaired. We are going to put the O's around it. Okay, so valence electrons, what do we have? So we have nitrogen, which has 5. Then we have 3 oxygens, which each have 6. And then we have that negative charge, so we need to add an additional 1. So we have 24. Okay, if we wanted to give everything a full valence shell, we have 4 atoms. None of them are special ones, so 4 times 8 is 32. So difference between 32 and 24 is 8. We need 4 bonds. So there's 1, there's 2, there's 3, and here, as going to be our fourth, right? We need 4 bonds. So if you think about nitrogen, if I were just drawing a dot diagram for nitrogen on its own, I would draw this. So generally you would expect that nitrogen would do 3 bonds because it has 3 unpaired electrons. But obviously when we look at this, it's lost its lone pair. The reason it's lost its lone pair is one of these oxygens was like, oh, you have a pair of electrons, here I come. And then I have my 6, and look at that. Now I have 8, yay for me. So now it's full, okay? One of the oxygens came along with its 6 and said, hey, let's make some pairs here, right? So it paired both of those, but I don't really want to draw them like that because we don't draw them like that. So I'm just going to shift them in a little bit to draw them together like a double bond, right? So there's that O. And then our other O, right? It comes along. But the thing I have to remember is I have this negative charge, which means I have an extra electron. So there's that extra electron. And now here comes my last O with its 6 electrons saying, excellent, you have another lone pair that I'm going to mooch off of. So here I come. So this O donated nothing to the pair. This O also donated nothing. This one did actually go about sharing, right? So again, it doesn't really matter for your diagram. You're still going to come up with it the same way. More so just a matter of recognizing for some of you who get really bothered by like, this isn't doing what it's supposed to do, and I need to know why this isn't doing what it's supposed to do. Coordinate covalent bond is usually the answer to your question. Some of you are probably sitting there thinking, I never was bothered by it. I never noticed it. And honestly, I wouldn't worry too much about it. We're not really going to ask you, where's the coordinated covalent bond? It's more just an explanation because some of you guys get thrown off when something does something that doesn't go exactly according to plan. Now I better pause and plug my computer in because apparently it is going to go to sleep if I don't do that. So 2 seconds and we will continue. Okay, so next type of diagram is what we call a structural formula. So you're going to find the more Lewis dot diagrams or electron diagrams you do, the more they kind of get annoying because there's a lot of dots to draw. So a structural formula is kind of the next step from a dot diagram. So what's different in a structural formula is we are going to replace bonding electrons with lines. So one pair of bonding electrons, so a shared pair, is going to be represented by a single line, where that single line represents a single bond. Okay, a double shared pair, or 4 electrons being shared, which means 2 shared pairs, is going to be represented by 2 lines. And then a triple bond, which means that we are sharing 3 pairs of electrons, is going to be represented by 3 lines. Okay, you're going to find that when we do structural diagrams, we generally do not draw lone pairs. The only exception to that would be a central atom. If we had a central atom, we would draw, that lone pair there. Okay, so let's look at an example of what this is going to look like. You are still generally going to find that you have to draw your Lewis dot diagram first. And the reason you still have to draw a Lewis dot diagram is you need to know how many bonds there are, and you need to make sure that you've drawn that molecule correctly. If you try to skip that step and go straight to a structural, sometimes it works, but a lot of the times it doesn't because your structural doesn't actually match up. And if you actually figured out how many electrons you had, you'd see that it doesn't work out at all. So let's look at SO2. So SO2, the S is going to go in the middle, and we are going to put an O on either side. Those are kind of super wonky placements, so let's fix that up a bit. Okay, so I still want to start by doing all the things I need to do to make sure that my diagram actually works. So first thing I want to do is I want to figure out how many valence electrons. So sulfur has 6, And then I have two O's, each at 6. So we are allowed to have 18 dots in our diagram. If we wanted to do a full valence shell, we have 3 atoms that all want 8. So 3 times 8 is 24. The difference between that is 6, and that means we need 3 bonds. So 1, 2, we need to make a double bond to make it work, right? We now need to fill shells. So 1, another pair, other pair, that gets my O to 8. Sulfur has 2, 4, 6, so it needs a pair, and this oxygen has 4, so 2 more pairs. Okay, so we wind up with that. So make sure it works, right? Everything has a full valence shell. We have 2, 4, 6, 8, 10, 12, 14, 16, and 18. So we have 18 valence electrons. So now we want to turn this into a line diagram. So we still have the S and the O. So we are going to replace these with lines. So because this is one shared pair, it's a single line because it is a single bond. Because there is 2 shared pairs here, it is a double bond. So we are going to put 2 lines. Okay, we said we weren't going to show lone pairs on non-central, so we're not worried about the dots on the O. But we are going to show the lone pair that's on the central atom. So the sulfur had 1 lone pair, so I draw 1 lone pair. And the reason we need to draw that is we're eventually going to get into 3-dimensional shape, and the lone pair on the central atom matters, but the lone pairs on the non-centrals don't, okay? So much faster to draw this than this, but you have to know what this looks like to actually be able to go about drawing that structural diagram. So we spent time talking about ionic bonding and covalent bonding. A type we haven't talked about yet, though, is metallic bonding. Okay, we are not going to ask you to draw metallic bonding because these diagrams look completely different. So when it comes to metallic bonding, we use what is known as the electron C model to explain metallic bonding. So metallic bonding works completely differently than all of the other ones, okay? We're still trying to get a full valence shell. That doesn't go away. But what's different is how we go about doing it, right? We said in ionic, we would gain and lose electrons to get a full shell. We said in covalent, we were going to share. In the case of metallic bonding, that doesn't really work anymore. So instead, what you find happening, and you'll see as soon as I show you the picture, this is why we don't ask you to draw this, right? We're not going to ask you to draw this. So how we get a full valence shell in metallic compounds is they basically lose their valence electrons. Doesn't mean they go away because they can't just go away. Instead, what happens, and why we call it the C model, is our electrons basically make up what we call the C. And you can think of all our metal cations as basically being rocks on the shore, right? And as the waves come through, they pass by and then they go back out. So what happens is these positively charged ions at times are going to be surrounded by a whole whackload of electrons, and at times they might be surrounded by none. But this is how they go about gaining a full valence shell. So all of our metals, right, and they're all attached together, right? You've used aluminum foil before, you've seen a sheet of iron, like you've seen like copper, you know that they do bind together. But what we also find is most metals, not all metals, but most metals have the ability to conduct electricity. And you think back to when we were in solutions, we said you can conduct electricity if you have charged things with the ability to move. Well, we have charged electrons and they're able to move all around these positively charged ions. And electrons are what create a flow of electricity, which is why most metals are able to conduct electricity. Okay, this is also why you find that a lot of metals, when they are stretched thin enough, are going to be quite malleable, right? We always talk about how metals are malleable, ductile, and part of that just has to do with how it's all put together. So you will not be asked to draw metallic bonding. You might be asked to recognize that we use the electron C model, which is that all the metal atoms lose their electrons. The electrons basically create the sea, and that sea of electrons are shared amongst all the metal ions. And we might ask you to recognize, like if we gave you some formulas, so like NaCl, oh, that's ionic. And then if we gave you like Na on its own, oh, that's a metal, so it must have metallic bonding, okay? So that's kind of what we're going to ask you about that. Recognize that it is a thing, recognize that it's different than ionic and covalent, but yeah, we're not going to ask you to draw this whole thing out, okay? So yeah, that would be the end of this lesson. For the most part, what you should continue working on is just some of those diagrams, working on some of the structural stuff, making sure that you feel really comfortable with all of those covalent diagrams before we start getting into some of the more complicated stuff which requires it. So we did the Lewis dot diagrams, now we're looking at structural, and then we're going to keep building on that.